All right, so this is the last module of this short course. Um, we end on the topic of, do polls, right, influence respondents or voters, right? So when they see reporting about polling, does it affect their opinions on issues, and does it influence their voting behavior, right? And then a very big sort of question regarding democracy. We know, well, we hope that elections help influence public policy and keep elected officials accountable and responsive. And even though we have frequent elections in the United States, compared to most Western industrialized democracies, we have very frequent elections and we vote for a lot of offices, even dog catcher in some counties, and judges at the state level in many states. Um, in between those elections, we might hope that public opinion polling may influence elected officials. And the four articles that we are assigned basically say yes to both these questions, but obviously in a more complicated manner. I'm not going to spend a lot of time. The articles, I think, do a better job explaining those. Luckily, two of those articles are pretty short. So the reading burden for this last week isn't too bad. What I'm going to focus on is regression analysis. One, because your replication project involves you doing this, but also many of the studies that we've read and many studies that you will read in the future, academic articles, will use regression. This is the tool, right? T-test, ANOVA, chi-square, very useful, and we've seen them used in the articles that we have read, and they're a great way to look at relationships, especially bivariate relationships, to start to understand the data that you have. You don't just jump into a regression. You got to look at the data, run some descriptive statistics, some frequencies, some averages, some standard deviations, some plots, some data, use some visual aids to look at the data, run some t-test or ANOVA or chi-square, and then when you know what your data looks like, you know which data sets are dichotomous and which ones are interval and which ones are ordinal, and you've seen the missing data, the don't knows and the refuses, and you've coded those, then, right, you're ready to run an OLS regression, right? And this examines the strength in the linear relationship between two variables. At least the bivariate regression looks at two variables. But multivariate regression also looks at the relationship between two variables while controlling for other variables, but we'll get to that in a moment, right? One variable is specified as the dependent variable. It's usually the variable that we're interested in, and we want to explain variation in the dependent variable. So let's say we're interested in income. Why are some people making a lot of money? Some people aren't, right? That would be, income would be our dependent variable. The other variables would be explanatory variables, often called independent variables. And obviously, what's related to income? Age, education, family income, gender, race, you name it, right? And so that's just the basics of regression, right? And you're going to need to replicate a regression in the Shackelford-Besser article. And so let's talk about sort of what you're going to be doing, right? Depending on if you're reading a textbook or an academic article, sometimes an academic article will just say, we're using OLS regression, ordinary least squares regression, and they don't show any equation, but often they do, And it depends on if you're looking at an economics article or a psychology or political science or a math article, they may use different notation for this exact same technique and linear relationship, right? So the top one is E, expected value of y given x, equals alpha plus beta times x, right? Alpha is the constant, beta is a regression coefficient or slope, x is the independent variable, y is a dependent variable. So the expected value of y given x is equal to this linear relationship, which is identified as a plus bx, right? Alpha plus beta x. But another article might say y hat, which is also the sort of predicted value of y. That's how we interpret that, equals a plus bx. And again, you might add the e, right? Or epsilon sign, which counts as error. So instead of a constant alpha, you might have beta naught, beta 0. So all of these are the exact same notation for a linear relationship. And the classic, if you remember taking algebra in a math class, y equals mx plus b, where b is not the regression coefficient, it's actually the constant. And m is the slope, right? Whereas the above equations, the beta or b are the regression coefficients, also known as a slope. But for our article, right, that we're replicating, they do lay out an equation. Y equals b naught or beta naught, which is sometimes referred to as alpha, or constant. In some math problems, could be even another notation, but these are the most common. So y equals a constant value, sort of a benchmark given what y equals when x equals 0, and then the slope of x1, the slope of x2, slope of x3, right? That all the betas, right? 1, 2 are the slopes which indicate the relationship between. So beta 1 will indicate the relationship between x1 and y. x1 represents education level, right? Beta 2 represents the slope, which is a measure of the relationship, linear relationship of x2 with y, and x2 is age, and so forth, right? So just want to make sure you sort of understood the notation of a linear relationship in math and statistics. So in this relationship, y is the dependent variable, a is the constant, but it could also be b naught, right? Beta naught. B or beta is the regression coefficient, sometimes referred to as a slope. X is the independent variable. E is the error term, which is the difference between the observed actual data point and what our linear regression model would predict given the value of x. And usually there's a difference. It's rare that our predicted value of y actually matches the actual value of y. But on average, it gets pretty close, right? If it's a good model, a good fit. So, right, here's the mathematical equation, right? Y equals mx plus b, y equals the slope of x plus the constant, right? And this slope is really the rate of change. As x increases, what happens to y, right? And we see as x increases, y increases. This is a positive linear relationship of x and y, right? As x goes up, y goes up. Not by the exact same amount, but pretty consistent, right? At least that's what our model's predicting, right? And that's what the slope is. And so the slope of the regression line describes how much we expect y to change on average for every unit change in x. The intercept is a necessary mathematical descriptor of the regression line. It does not describe any specific property of the data or any particular relationship, right? So we have the dependent variable, which typically should be interval level, but we talked about this before, and many studies that we looked at sort of cheat on this, but the rule of thumb that I was taught ages ago was that if you have a ordinal measure that has seven categories, mathematically it starts to act like an interval level measure. I found another study that said if you had an ordinal measure of 10 categories, then it acts. But I think even Biggers and Bowler and some other studies, they had 6 categories. So they fudge a little bit, right? They fudge. But typically, what my mentor said is OLS regression, even when you violate some of the assumptions, um, typically gives you robust findings that are fairly accurate. But you could do an order logit, right, or some other technique. But OLS is pretty flexible, even if your dependent variable is not perfectly interval, right? So if you have 7 cases, 7 categories in ordinal, you probably could treat that as interval and run OLS regression. And A is the intercept, B is the regression coefficient, right? X is the independent variable, Y is the term, right? Y and X are the real data, they're observed, right? Whereas A, B, and E, right, the constant, the slope, and the error term are all estimated through the statistical technique of OLS regression. Y and X are the real data that you plug in to SPSS or any statistical tool or any, equation, and they're going to estimate A, B, and E for you, right? So the slope can be called the regression coefficient for the predictor. It can be called the slope or the gradient of the regression line. It also can be called the rate of change, and some people refer to it as just the direction or strength of a relationship, right? That's how often this beta is described. And A is simply the intercept, where really it's the value of y when x equals 0. It's a point at which the regression line crosses the y-axis, and you pretty much ignore it. It can have wide different values, and it can even have values that don't make sense because x in your data, your data set might not actually have a value of an independent variable that reaches 0, but right, the intercept is theoretically the value of x when x equals 0, even if your data set doesn't contain a value of 0 in your data for x, right? So, if you had a negative relationship, right, as x increases, y decreases, you would have a slope that's less than 0, that's negative, right? And it would start sloping down to the right. If you had 0 relationship between x and y, there's no relationship, 2 random variables, right, that have no relationship, then beta, right, the slope would equal 0, and you would have a straight horizontal line, right? And then if you had a positive relationship, as x increases, y increases, you would have a slope that is greater than 0, that's positive, right? So here's some fake data. Imagine a selling price of a home, right? And looking at how the size of the house reflects the price. Clearly you would imagine that a larger house would go for more money, but obviously there's other factors as well. So we plotted this theoretical data, right? It would look like this. So if you plot these data points, house size in square hundreds of feet, and the price in thousands, right? So 89,000, 89,500, 79,900, and we plotted it, it would look like this. And it looks a little kind of random, but if you ran OLS regression, it would attempt to draw a straight line that best fit this data. And you can sort of see, right, as x, the house size, increases, y increases as well, the price increases as well. Not perfectly linear, but it might be a decent way to describe this relationship. This linear regression might be a decent way to look at how house size influences price. Not perfect, right? Actual real world data. I'm not a sports fan, but I go to games every now and then. And I really enjoyed Moneyball, the Oakland A's, which are moving to Las Vegas, which is good news for people here in Las Vegas. But this is a published academic journal article in economics, actually, if I remember correctly. And they analyzed baseball and soccer. And here's some baseball data. And they basically took the average annual salaries of all the players and the team payroll for a 20-year period, right? And then the average percentage winning, right? Winning percentage, right? And then they plotted it. And you see, this is a pretty decent fit, right? It looks pretty linear, right? And those darn Yankees, they have a lot of money and they have a large payroll and they win a lot of games, at least from 1980 to 2000, right? Florida, not so much. And Moneyball, right, was this great movie with Brad Pitt. I liked it, where they had the Oakland A's had a very modest payroll and they were trying to figure out through statistical analysis to identify people that got on base, but they were sort of they weren't very good looking. They might not be in the top physical peak, but they got on base, which means that you have a better probability of scoring runs, and that's how you win at baseball, right? Rather than trying to get one big all-star that costs millions and millions of dollars to do. So through statistical analysis, they try to identify those individuals. And they tried to prove that even with a modest payroll, if you were smart, right, you could identify players and be competitive. The problem is then the other teams with a lot of payroll could do the exact same. They could identify statistically who can get on base, and they can pay the big all-star that hits grand slams and attracts a lot of audience members. They could do both, right? That's the problem. But at the time, right, the Oakland A's were experimenting and not just looking at the gut feeling. There's a great scene where they're around the table and they're like, yeah, he looks great. He swings that bat. You hear that crack. All of these sort of gut feeling, these experts, these scouts, where they thought they could personally identify someone who's going to do very well in Major League Baseball, and really they weren't doing that great. They were looking at the person as handsome, had a certain body type, and all these biases in what they thought were a good baseball player. And the point of Moneyball was that you can't always determine that, right? And you can do it with numbers, right? And that's the magic of statistics and why I love statistics, right? So here, that's real data, and that's clearly a linear relationship, right? Money and winning, right? Now, when you look at every year, any given year, you could see a lot of fluctuation where the best payroll team doesn't do that great this particular year, but this is 20-year average, right? And therefore, you see how money in the long run really influences winning percentage, right? And so I think plotting the data, running a regression can help us analyze relationships. And so the question is, how do you draw a best fitting line, right? How do you do that? Well, what you do, right? What you do is you use calculus basically, and calculus attempts to draw a line that minimizes the difference between our predicted values, which are all that basically we predict all the points are going to be on that straight line, but the real data, right, which are in green, only one of those data points fall on that line. Some of them fall pretty close, and a couple of them fall fairly far. But what regression does using differential calculus, which you can simplify and actually do some simple algebraic math to create this line that reduces the squared sum differences of the observed versus the expected predicted value of y, right? And what we know is that there is a unique line that will do this. And if you adjust this line a little bit off, you're going to increase the sum of the squared error, right? So the best fit means that the sum of the squared residuals, or the error, right, or the sum of the squared differences between the actual y, right, and the predicted y values are at a minimum. And that's why differential, this is a minimization mathematical problem, And if you remember your calculus, that's differential calculus, and differential calculus can solve a minimization problem, right? And in some graduate classes, I'll have people do this, and it's not that hard. The math is not that difficult. I could walk you through it. But SPSS does it for us, and why would we waste our time? And it's only doable if you have a small number of cases. If you have 1,000 cases, it could take you a very long time to run differential calculus on a large number of cases, right? So usually when I have students do this, we'll do like 10 cases, right? 10 observations. So again, the least squared regression line is this unique line where the sum of the squared vertical distances is the smallest possible, minimization. There's different types of regression, right? You have simple, such as a bivariate regression, where you have dependent variable y and one explanatory variable. In some cases, you have more than one explanatory variable, more than one independent variable. We call that multiple regression. In some cases, you have a bivariate regression that is a linear relationship. That's probably the simplest regression model. But in some cases, you have a nonlinear relationship. And so for with the multiple regression, you have linear multiple regression, and then you have multiple regression that's nonlinear. So we'll take a look at some examples. Imagine we have data set A. That looks like a pretty clear linear regression, and so that's appropriate. Set B looks like curvilinear, maybe even quadratic, right? So OLS would not be appropriate. Set C looks as if we have almost a perfect linear relationship with one outlier, right? And that's interesting because what do you do with that outlier? There was a great book, State House Democracy, which actually is very relevant to this topic. Erickson and McIver, I believe, wrote this. State House Democracy. It's decades old. But they looked at the 50 states and to see if public policy in the 50 states seems to match public opinion. So is public opinion in the 50 states a good predictor of what states are doing when it comes to like welfare and abortion and other things like that, right? And what they admitted right from the start was we look at the 50 states, right? In fact, they may have looked at the continental U.S. if I remember correctly. So they didn't look at Alaska and Hawaii because not a lot of public opinion data was generated back then for those two states because of different time zones and different reasons, right? So they looked at continental U.S., 48 states, and they start off in the first chapter saying, we have one outlier that is messing up our regression equation in our models, and it's Nevada. They're just weird because they are fiscally conservative but socially liberal with legalized brothels and 24-hour access to alcohol and whatever, strip clubs and blah, blah, blah. So socially liberal, typically, but fiscally conservative. And so we throw them out. So really, I would say that in data set C, that observation, it could be an error. Someone input it incorrectly. I think the very first data set that we played around with, some old GSS data, has a variable, how much TV do you watch a day, any given day, how many hours do you watch? And one person in that 1,400 data set, right, 1,400 people, respondents, said 24 hours. So it's possible that they're an insomniac, but it's also possible that they lied or someone entered the wrong information and maybe they said 2 hours and someone typed in 24, right? So could be reason. Data set D is basically X only has two values, right? A value of, let's see, 5, 6, 7, 8, 8, and a value of 19, right? Really, if you have an independent variable that only has two values, then one, a logistic regression or a independent sample t-test would be more appropriate, not OLS, right? So here, data set A, linear regression, I think perfect to run. Obviously, this is not a linear relationship. OLS regression is not appropriate, right? Some other type of nonlinear regression is going to be. One extreme outlier, you're going to have to look at that outlier and make a decision on whether you're going to include it or exclude it. And then data set D, X only has 2 values, and some type of redesign, a logit, a probit, independent sample t-test, something else other than OLS regression. So it's important to look at the data, plot the data, run some other statistical analysis before you jump into your OLS regression. And SPSS can do linear, nonlinear models, linear and nonlinear models, right? So you can look up that information to show how to do it. In fact, one of our articles, I think in Module 1, looking at partisan extremists, left wing and right wing, and are they associated? Are hardcore partisans cognitively inflexible? And they showed this through a nonlinear quadratic relationship, right? And we could replicate that using a nonlinear model, right? And SPSS has that option. You can do curve estimations. But what we're going to do is we're going to do multiple linear regression for your replication studies. That means more than one predictor, right? You're going to have more than one slope, more than one regression coefficient, right? And here, multiple linear regression, each regression coefficient is the amount of change in the dependent variable that would be expected per 1 unit change in X, right? If all the other independent variables in the model were held constant, generally held at their mean. But for dichotomous variables, that can be different. And so again, this relates to the article that we're going to replicate. So the function of multivariate regression analysis, you're controlling for the confounders, right? Other factors that might explain the dependent variable than the main independent variable that you're interested in to test your hypothesis. So education is associated with the dependent variable income, but so is age, sex, gender, other things as well, right? And as your explanatory, as your replication study is doing, right, you create an interaction term. And so multivariate analysis can test for interaction between predictors, right, and effect modification and modifiers. And that article on attitudes towards homosexuals has an interaction term, and you're going to do that for your replication study. I believe it's education times conservatism. Education ranging from whatever the minimum least educated respondent up to, I think they go up to 20 years of education. So 0 to 20 times a dichotomous variable 0, 1, whether you're conservative or not, right? And this clearly, multivariate regression analysis, improves predictions because you have more explanatory variables than simply bivariate regression, right? Bivariate regression can be useful to look at simple relations, right? So let's say the number of votes that a candidate gets versus the, let's say how that's related to how much money a candidate spends. And we've shown that money influences elections, but we've also found that it can be a complicated relationship in that candidates that are in trouble, right? They're in danger. They could be an incumbent, but they have a strong challenger, or there's a scandal. They end up spending more. And ironically, because they're reacting to a scandal, they get a lower vote share. So you find that some candidates spend a lot of money only when they're in trouble, right? Incumbents will spend a lot of money when they're in trouble. And then they get actual fewer votes than they did the last election when they weren't facing a good challenger or they didn't have a scandal and they spent less. So the relationship between the votes for a candidate and expenditure actually ends up being quite complicated. And one of my professors, when I was an undergraduate, Gary Jacobson, he made a big name for himself, sort of help explaining the complicated relationship between expenditures and vote share that a candidate gets. That people were looking at it back in the day in the 1970s and 80s very simplistically, and he's like, no, we have to have much more complicated models to explain how money influences the vote share for a particular candidate, because this could be misleading. It's a simple bivariate relationship. But what if we add another variable? Now, instead of 2 dimensions, we actually have 3 dimensions where a data point, the value for a dependent variable, could be associated and influenced by x1 and x2. So it actually can start to spread out a little bit 3-dimensionally, right? And multivariate regression does the math for us, right? I could have you do bivariate regression by math easy. All of you could do it piece of cake. And we could even do bivariate differential calculus to prove that our OLS estimates are a best fit, at least for small numbers. Once we get to multivariate regression, the math becomes much more difficult, and we need computers to do that, right? So here we could have X1 expenditures for a candidate, right, in its relationship with the number of jobs created in a particular year, right, and votes for a candidate, right? And we could start to see how these 2 explanatory variables help predict, right, the vote share for a particular candidate. And so here our equation is our dependent variable is related to a constant, beta naught. The hat is this is an estimated slope, right? Well, estimated constant. Beta 1 hat is the estimated slope based on the data for the relationship between x1 and y, the dependent variable. And beta 2 hat, the estimated slope, not the real slope in reality, but our estimated slope, reflects the relationship between the x2, the other independent variable, and our dependent variable vote share, right? And we see this area that helps get explained through multivariate regression, right? Beta naught is simply the intercept, right? And we have the slope for beta 1 and the slope for beta 1 and slope for beta 2, right? And you see that these 2 variables are causing a slight change, right, in y and influencing y. And they have a separate dynamic. They have a separate dynamic. And multivariate analysis can account for that. Another way we could look at this is to imagine that the slope, right, for x1, the regression coefficient, really is looking at how the independent relationship between x and 1 while holding x2 constant. And we're trying to account for the amount of variation x1 explains in xy, the independent variable explains in the dependent variable, but not including x2 and the amount of explanation that it takes on in the dependent variable. So we want to have beta 1 looking at just a relationship of x1 and y while holding x2 constant. And beta 2 does the exact same thing. And what we have is the center is discarded because we can't say which variable actually accounts for the amount of variation in the dependent variable. We're excluding, right, the covariance between x1 and x2 because they're going to be associated, right? And so multivariate regression does all this complicated math to identify the independent relationship that's independent from x2 and other variables, how much variation x1 is accounting for in xy, and how much variation, right, x2 is accounting for y, and we can go so for x3, x4, right? And the more variables you throw in that are related to y, the more variation you're explaining in our dependent variable. And it would be great to be able to have enough independent variables that are strongly associated with y, where you could explain 100% of all the variation in y. That never happens, right? But the more variables that you have that are related to the dependent variable, the more variation you are accounting for. And we measure that with r squared, which we'll talk about in a bit. So what I did is, instead of replicating the polling project for you and showing you exactly what to do, because I want you to experiment and sort of start fresh and tackle that sort of blind, which is not fair, but you kind of learn by doing this. I am going to do an OLS replication for one of the articles that I assigned. So this is a great article because, one, my mother's Swedish, and two, we've read so much about American polls, right, and survey experiments of American students, whatever, that it's nice to get a little bit different. So we have some international studies in our last module, right, to mix things up. But also, this is 6 pages, right? They keep it short and sweet, so much so that the first part of the study, where they run an OLS regression, they don't even show you the regression results, right? You have to look at an appendix that's online. So I downloaded the appendix, and here is the regression. So their very first step in analyzing the data is just seeing if elected officials in Sweden are satisfied with their party's polling given a certain type of treatment. Basically, they were sent a survey and they were given a treatment where their party was, hey, you know, your party is doing pretty good, or your party's not doing so well compared to 3 years ago or 2 years ago, right? When the polls had you up at that point. How do you feel, right? This is not their main hypothesis, but it's interesting because I think, one, it shows that elected officials care about polls and whether they're increasing or decreasing, right, support for their party. And I think also this test to see if are the elected officials reading the survey and understanding the survey and accurately giving a response. So in a very predicted manner, those people who are more satisfied with the polls, who answered more satisfied, right, in a very predictable way, right? So it seems as if the people, these elected officials taking the survey, are responding to the prompts as predicted. But again, this regression isn't proving that democracy works. I think what it proves is that the elected officials care about polls and they are paying attention to the survey, right? But this is the OLS part of the study, right? So like many studies nowadays, they provide supplemental files and replication files, often held at Harvard University, right? So I went there, downloaded the data. The problem is, compared to Biggers and Bowers' last module, their data is not perfect. They exclude a couple of variables in their data set that they created. Maybe they didn't want to share, or they forgot them, right? But most of the data is there, right? And the dependent variable is, right, how satisfied are you with the support your party has in public opinion right now? And so it ranges from 1 to 5. And again, they run OLS regression. Really, this is an ordinal, so you could do ordered regression. I think I remember they said they ran ordered regression and the results were pretty much the same, which again, my mentor, Max Nyman, would say OLS regression, even when you violate some of the assumptions, produces robust findings. He always said that to me, because I would be like, oh, well, we need to run this special regression because the data suggests we should. And he'd be like, OLS regression is perfectly fine. He was an old timer, right? He's still alive, hanging out. He's still publishing. But yeah, that was his generation. OLS regression is fine for any dependent variable. It's not always the case. It's not always the case, but he is right. OLS regression, even when you violate some of the assumptions, provides typically robust findings that won't change even when you do something more fancy, right? It's not always the case, not always the case. So here's the dependent variable. The main independent variable is the treatment. they give different frames related to the last module, right? Framing sort of their reality is like, hey, you're not doing so well compared to this poll. Or, hey, you're doing pretty well compared to this other real poll. And they have these loss gain frames, right, for 7 different parties. So a lot of different treatment effects here going on. But basically, did they get a losing frame or a gains frame, right? And in the appendix data, you can look at what reference point they're comparing to. Hey, you're polling at 6.1%, but, a couple of years ago, you were polling better, right? So you kind of lost. How do you feel? How do you feel, loser, right? So they do this. So they present this data in the appendix, not in the article. So you're not going to see this unless you download the appendix. And I put that in the module. And then the control variable is the party winning or losing in the recent election? Specifically, they create a dichotomous variable whether they're currently losing. The problem is that it's hard to measure this to know what they did. It wasn't in the downloaded data set, so I had to create this, right? I had to create this. And, clearly the center party is not doing as well as the moderates, which is actually a conservative party, but they're called the moderates. But they would be identified as a conservative party by most comparative scholars. But really, I think what they were doing, right, was not that, oh, the center party has less. It's whether they were on the uptick or the downturn, right, in polling. Because in the appendix, they showed this information. So my presumption was that you're winning if you're on the up curve and you're losing if your public opinion polling is going down, right? So I created a dichotomous variable based on this graph, right? Totally guessing because this 6-page article doesn't provide a lot of detail to be able to replicate. So, but I'm doing the best I can. And then another one, yes, another control variable, sorry, I forgot. So the dependent variable is satisfaction with the polling of their party. The main independent explanatory variable is the frame, losing frame or winning frame. And then a control variable. How many months ago was the reference poll? So they actually pick a real poll where they can compare the current poll to show whether they're winning or losing. Sometimes they had to go back several years. They did not say in their article, unless you can find it, if you can, please let me know, what year their data came from. I believe the panel of politicians done by the Swedish university, Gothenburg University, if I remember correctly, they do this survey twice a year, but they didn't identify, and I could not locate the data panel of politicians to sort of identify which survey they looked at. So just my best guesstimation was that they analyze their data and did their survey with this experiment sometime in 2017. So based on that, I could count the number of months from their current survey, 2017, that's my guess, compared to the reference point. And so I created that variable, and I think I got fairly close. And we already talked about whether they're winning and losing in recent poll, right? And we can do this OLS regression pretty easy. Go to Analyze, right? Go to Regression, right? You're not going to be able to do this right away because you would need to create the months and the losing variable. I can upload what I have, what I created, which I added to their replication data. So what I'm going to do is I go to Analyze, go to Regression, choose Linear. I then put in the dependent variable for the dependent variable slot. That satisfied polls. All the recoding is already looks good. The missing is missing, and it ranges from 1 through 5, right? Which is more ordinal than interval, but it's okay. I'm replicating this. I would probably do an order logit or order probit, but OLS regression is probably fine. Then the months variable that I created, the losing and recent poll, which is dichotomous, whether their polling is on the downturn or the upturn, and then the treatment, which is a variable that's available in their data set, right? So I had to create two of the three independent variables, right? And then I just clicked OK. I didn't mess around with any of the statistics or plots. You could look at the plots and the residuals to see if this is a true linear relationship. This class doesn't have time in 7 weeks to teach you everything about regression. This is a crash video on regression, OLS regression, right? So I'm not playing with any of those, but you could add some statistics, you could look at some residuals, you could plot some residuals to see if truly this is a good model, a good fit, and a good linear fit. But we're just gonna press OK. And what we find is that these three variables account for, if you look at the R square, that's interpreted as 17.6% of the variation, which is not bad for survey data. So really, these three variables account for about 18% of the variation in variation of whether a elected official in Sweden says, I'm very satisfied with the polling, or I'm not, right? Obviously, there's some elected officials like Donald Trump or anyone who's losing who sometimes they say, I don't care about polls, right? So you might get some of that. But you find that there is a statistically significant relationship between the treatment, whether it's a losing frame or a gaining frame, and their answer to the question, how satisfied are you with the polling of your political party, right? And months matter, right? The number of months that a reference point is referred to clearly sort of reduces the impact of some of these results. And then, of course, if you're currently losing, right, then you are more likely to say that you're less happy with the polling, right? So all three of these variables, the number of months of their reference point, whether they're losing in recent polling on the downturn or upturn, and then the treatment frame, if they're given gains or losses. And so if they're given gains treatment, they're more likely to say that they're satisfied with the polling of their party, and no surprise if they're getting the losing frame. We could also create an interaction term of treatment and months. They don't do that, but that might be something interesting. The longer the reference point, the treatment would have less of an effect, right? So does this data match the results shown in the article, or at least in the appendix? Not really. Surprisingly, my guess at when they did the survey, what year they looked at of the panels of politicians survey data, where they provided an experiment to the Swedish elected officials, that guess was a good guess. So that is almost spot on. My guess as how they measured whether a party is currently losing in the polling wasn't as good. And of course, the treatment poll was pretty spot on. So if you look at the months between poll and reference point, my regression coefficient, my slope, spot on. Their regression coefficient for losing the recent poll is positive, statistically significant, but a little bit larger. Mine was 0.7 something. And then my regression coefficient for the gains treatment, right? They are more likely to say a 1 or a 2 or a 3, right? Meaning that they're more satisfied. My result was negative 0.62. So very, 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 very close, right? So not actually having two of the variables, and I had to recreate that data really through guesstimation. I got pretty close. So I think their replication file is not very good. I could have contacted them and said, hey, could I get these variables? But that would have taken too long and I'm too lazy. And I thought it was fun to try to approximate. So their replication file is pretty sloppy, but I'm confident that they didn't lie or cheat because I pretty much could get their same results even not knowing exactly, but trying to piece together how they did it. So again, I think they did pretty much everything correctly. They're not lying, they're not cheating. That's a good thing. Most academics, I think, are honest, although when I teach research methods, I assign an article that has all these historical cases. A lot of them are anecdotal, but a lot of great anecdotal stories of tenured faculty getting caught fabricating data, right? And again, we don't know if they fabricated or not some of the data they could have, but so far I'm pretty trusting in their results. But it's a great article. Maybe I'll put it up if I can find it again, where just some classic stories of people, big names, some big names, tenured faculty. They get a big grant. There's pressure on them. They want more grant money in the future, and so they start to fabricate data, and they get caught. I'm sure lots of people who fabricated data didn't get caught, but these people did. And if you get a federal grant and you fabricate data, that is a federal crime. And these tenured faculty member served prison time in federal prison, right? So, moral of the story, don't cheat. It's harder to cheat now, I believe, given this culture of replication, which I love because I can really understand an article better when I get the data and try to replicate it and I really understand, and it gives me new ideas on, hey, if I was going to do this, and maybe I will do a similar topic, I would do it this way and it would be better, right? And I only really can identify that by getting my hands dirty with this data, which I hope is one of the things you kind of learn